Recording in progress. This is homework for part A. We're going to start with looking at the diffusion coefficients, right? So when we're doing a problem, typically we can assume, right, that it's going to be 10 to the fifth meters squared per second for a vapor, right? That's just the order of magnitude, right? And for liquids, we're looking at 10 to the negative fifth, 10 to the negative ninth meters squared per second. Now, this assumption always doesn't always work, right? And so what we want to do is look at different ways we can figure out the diffusion coefficients, right? So for a vapor, we can look at the Leonard Jones potential equation, right? And so what that is, so our diffusion coefficient of A to B, right? That is going to equal if I can get this to move here, that is going to equal that's going to equal 0.00266. This is a experimentally determined value, right? This is just a random number that they made up. This is experimentally determined, and that's going to be multiplied by our temperature to the 3/2 power, all over pressure times the molar mass of A and B, right? So basically the average times the collision diameter to the 1/2. Sorry, this molar mass is to the 1/2, right? And so this is the collision diameter of A to B, and then times our diffusion or our collision diffusion integral, right? And this is based off the boiling point, the temperature of the boiling point. And so we can use another temperature to estimate it, right? So T star is going to equal the Boltzmann constant multiplied by our temperature over our energy of collisions of A and B, right? And that can be used to estimate this this integral here with the boiling point, and this is actually squared here. And right, so this equation can be used to determine the diffusion coefficient for vapors. What you have to look out for is like our units, right? So this is going to be in bars, right? And so this will often be in centimeters squared per second, right? Instead of our meters squared per second. So next, what we're going to look at is liquid. So what we do for liquids, right? If we are working with a dilute solution, this is going to be used mainly for dilute solutions, right? We can look at the Stokes-Einstein equation, right? And so this is going to be our diffusion coefficient from A to B standard state, right? And so this equals our Boltzmann constant times our temperature, right? Over um, over 6 pi RA mu B. And RA, right, this is going to be our particle radius. And this is just our viscosity of B, right? And so this doesn't always work, or we don't always know everything here, right? And so what we can do is we can use the Vignes, I don't know if I just said that right, equation. Right, so what this is it's our DAB, right? So our diffusion coefficient, and that's going to equal diffusion coefficient at standard state multiplied by the or to the power of the concentration of the less concentrated mixture, if that makes sense, right? So if you have high concentration of A, it's going to be raised to the power of B, right? And then you multiply that of dBA to the power with A, right? And so these are often able to be found like online or in a textbook or something. And then you can use that and then plug this into, right, this DAB. And then with that, you will then be able to find this RA value. Right, so that's how you use the Vignes equation in tandem with the Stokes-Einstein equation to get your diffusion coefficient or your particle radius, right? So next, what we will do is we will move on and we're going to look at the continuity equation, right? And when we're looking at the continuity equation, we're going to be looking at our rate of formation, right? So this is our rate of formation. And this is a per volume value, right? And so the way we can kind of think about this is if we go back to fluid mechanics or thermo, right? We know the equation in minus out plus accumulation. This is our accumulation value, right? So this will be in minus out plus accumulation. Our RA is in turn our accumulation. So when we're looking at this in like a cube scenario here, let me draw this out. Oh wow, this is really good, ain't it? So pretend this is actually a good cube because it is not, right? So we have our flux in the z direction. This is z to dz. This will be y to dy, and then this will be x to dx, right? And so here we have our flux of A going through our cube in the z direction, and when it comes out, it will have a flux of NA z dz because it went through the entirety of z to dz. And so what we want to do here is we want to relate it to the continuity equation, right? So if we remember the continuity equation, that right, we've done this before. That's the gradient times our flux plus the change in concentration over our change in time minus our rate of formation, and that equals 0, right? And so we want to be able to relate this scenario here. So we want to write an equation here, right? So we're going to use this here. So our n value, right, that's our NA Z. And then we need to multiply it by our cross-sectional area, which is going to be our dx dy. And then minus our out, which was NA Z dz, also multiplied by our cross-sectional area, dx dy. And then our accumulation rate, that's our rate of formation. So that is going to be RA dx dy dz, right? That's our volume. We don't want it in terms of volume, right? So we have to multiply by our volume to negate because RA is in terms of volume, and that will equal our driving force, right? And so for this, our driving force is our concentration, right? So our change in concentration over change in time, right? And so with this, I actually have to move this here. This concentration is multiplied by our volume, dx dy dz. Sorry that that's all cramped. So the first thing we want to do in order to simplify this is divide by our volume on both sides, right? So that leaves us with Na z over dz minus Na Z dz over dz plus our RA equals our delta CA delta T, right? And so this can be simplified further by changing up here, right? Or by combining these two terms, we have Na Z minus Na Z dz all over dz plus our RA equals our delta CA delta T. So we look at this term here. Well, that's just the change in the molar flux from Z to dz, right? So we can rewrite this as d n a z over dz plus RA equals delta CA delta T. So if we move all this over to one side, we get 0 equals our delta CA delta T plus our dN A dz minus RA. And so when we compare it to this equation up here, right, it's a little bit different. But we know that this delta can just be written as dCA dt, right? So that is the same as this term up here, right? And the other big thing that stands out is this isn't a gradient of Na, but it is the gradient, right? Because our d over dz is just our gradient, right? So it's our gradient of Na, right? Because this gradient is d over dz, right? So in the end, we can write this as 0 equals dCA over dt plus our gradient of the molar flux minus our rate of formation. And that is our continuity equation. Right. And so following this, we can look at when we have a system here, right? So let's say we're equimolar, right? And we have, that's terrible. We have a vapor bubble and it's inside of liquid, right? So this whole outside area will be liquid. We know that this surface here is going to be at equilibrium, right? And so when we look at this, right, as this vapor is going up in the liquid, it is going to be producing the heat of vaporization as it mixes with the water, right? And so as the vapor condenses, right, it is releasing the enthalpy of vaporization. Well, in turn, that enthalpy of vaporization is then vaporizing the liquid, right? So you're in this kind of state of equilibrium between the two, liquid and vapor, because as you condense, you're releasing the vaporization, but then that vaporization is causing the liquid to turn into vapor, right? And so when we look at that, right, we know Na times delta H, well, let's do Nx, right, for the liquid, minus our Ny times vaporization, right? We get this. This is just going to cancel out because you're at that constant state of one is going out while the other one's coming in, right? And so you can neglect the delta H of vaporization, right, or enthalpy of vaporization, and that is why this is just at an equilibrium. So when we look at non-equimolar things, right? So let's say we have a system of A, we have 1A to 2Bs, right? Well, when we look at the flux, right, we look at flux a lot in homework 3. We know that Na plus Nb equals our overall flux, right? And so what we can do is we can look at this to get 1B, right? you need two A's going in the opposite direction. Well, two A's going in the opposite direction, that's just a negative 2Na, right? And so when we look at this, we can then plug this in, right? This should be NB. We can plug this in to obtain our overall flux, right? So we have our Na plus our negative 2Na, right, equals N. Well, now we see this, right? Negative Na is our overall flux for this. And that makes sense because the opposite of our Na, right, is going to be our flux. And this can be done for every difference in concentration, right? So if we look at this, another scenario, right, we have 3A to 1B, right? This is a lot different here. Well, we know our Na plus our Nb equals our N, right? And so Nb equals negative 1/3 Na, right? Because you need 1/3 of your A going in the opposite direction to get your B, right? So we plug that in, Na plus our negative 1/3 Na equals our N, or our N then just equals 2/3 Na, right? And so that means that 2/3 of our molar flux of A will then equal our overall molar flux, right? And that makes sense. And we can do that for any non-equimolar system, whether it be 43A to 23B, right? It doesn't matter. We are able to then use algebra to then get that, to find how our Na compares to our overall molar flux.